In this video, we will learn how to construct a confidence interval using the HTG hypothesis testing guide form. The problem here says if n equals 410 and p hat equals 0.84, find the margin of error at a 90% confidence level. Okay, so the main thing we're trying to do is find the margin of error. The margin of error is calculated using a formula that basically simplifies in general to the critical value times your standard error. So if we can sort out the information we have here, we can calculate those two things. So the critical value is, in my opinion, the easier step to start with. The claim here, we don't know. So we'll just assume whatever it is. We're not concerned about context right now. We're concerned about the mechanics of finding the margin of error, calculating the margin of error. And we have been given a confidence level of 90%. So with a 90% confidence level, that could be written as, well, it's written as 90%. Your alpha will be equal to 1 minus that. And that's 10%, obviously. As a decimal, you want that to be 0.10. Remember, 3 decimal places. So 0.10. Now, in each area, you're going to have half of that because confidence intervals are always two-tailed. Now, the critical value will be the absolute value of the boundary that would have 0.05 in the left tail. So in the left tail, we're going to find a z-score boundary because this is a claim about a proportion or a confidence interval for a proportion. And notice that on our quick reference guide, when we're doing a confidence interval for a proportion, we use z-scores for the critical value. And likewise, if we do a hypothesis test, our test statistic will be a z-score for proportions. So knowing that we need to find this critical value z alpha half, that's what we're doing now. We're using this area that's half of the total alpha, and we're going to use it to find a z-score. Norm.inverse is used for finding boundaries under the normal curve, and it requires a left-hand probability, which we have here, 0.05, the mean of 0 and standard deviation of 1, of course, because it is a z-score boundary that we're giving it, or that we're looking for, rather. And the absolute value is, I just have it on the outside because I want this to be positive. And I don't need cumulative here. I think that we're good there. So here is my critical value. Now I'm going to need that to calculate my margin of error. And I'm also going to need, let me show you this bigger for a moment. So far I have the z part here, and now I need the square root of p hat q hat over n. Now this whole section right here to the right of the plus minus sign, that is our margin of error. So we just need to now calculate that, and we'll call that the standard error. So we have a critical value that we just figured out up here. Make sure it's positive. It has to be positive when you're calculating the margin of error, because margin of error is a distance. Then we want the standard error using this formula here, the square root. And then we need a p hat and a q hat and an n. Well, p hat is your sample proportion of successes. Q hat is your sample proportion of failures, so they are complementary. If you add them together, your p hat and your q hat will equal 1 when added. And n is your sample size. So we will get the rest of the information. Oops, this is not the screen I wanted, sorry. Get rid of that. We have the p hat given here, 0.84. So if your p hat is 0.84, let's go ahead and type that in, 0.84, then what would your q hat be? They have to add up to 1 So 1 minus 0.84 would be 16. So we're going to multiply this times 0.16, and we'll make that a 0.16 just to be clean, and divide by the sample proportion, or I meant to say the sample size, which is 410. 410, and all that is being square rooted. So, now that I have that, I can multiply them together to get my standard, or I meant to say my margin of error. Multiply the critical value times the standard error, and that will give you a margin of error to add and subtract to your sample proportion. So the sample proportion that was given was 0.87, right? Or was it 0.84? It was 0.84. So that is our point estimate. Our sample proportion is the best point we have to estimate the population proportion. The margin of error we just calculated above. So that's one way of stating the confidence interval. We could say with 90% confidence, we believe the mean will fall. We have 90, let me say that again. We have 90% confidence that the mean, the true population mean, will be within this range. And it's interesting that we don't have enough decimals showing here, so let's put a few. Okay, now your parameter symbol is what you're estimating. So in this case, it's not the mean because we're talking about proportions, so it should be P without a hat. If it has a hat on it, that's the sample statistic, and we don't want that. We are estimating the population proportion. The lower boundary would be the point estimate, the sample proportion minus the margin of error, and the upper boundary would be the sample proportion plus the margin of error. And so I think we've finished this problem now. Let's see. It says just to calculate the margin of error, we didn't even need to go ahead and get the boundaries of the interval. So to 3 decimal places, our margin of error is 0.030.